When we look up at the night sky, it feels almost inevitable that one day humanity will travel between the stars. Science fiction has filled our imaginations with massive starships, warp drives, and civilizations spread across the galaxy. From Star Trek to Interstellar, the idea that humanity will one day leave the solar system and visit distant star systems feels almost like a natural step in our future. But when we step away from fiction and examine the actual laws of physics, the picture becomes far less optimistic. The reality is that interstellar travel is not just difficult. According to everything we currently know about physics, it may be fundamentally impossible for human civilization. To understand why, we first need to grasp the scale of the universe. Our planet orbits a fairly ordinary star, the Sun. The next closest star system to us is Proxima Centauri, which lies about 4.24 light-years away. A light-year is the distance that light travels in 1 year, moving at approximately 300,000 kilometers per second. That means the nearest star is about 40 trillion kilometers away. To put this into perspective, the fastest spacecraft ever built by humanity, the Parker Solar Probe, can reach speeds of around 700,000 kilometers per hour at its fastest point near the Sun. That may sound incredibly fast, but even at that speed, it would take more than 6,000 years to reach Proxima Centauri. 6,000 years just to reach the nearest star. And that's assuming the spacecraft could maintain that speed continuously and travel in the correct direction the entire time. But distance is only the first problem. The true obstacle is the speed of light. According to Einstein's theory of relativity, the speed of light is not just a suggestion or a technological barrier. It is a fundamental limit of the universe. No object with mass can accelerate to the speed of light, because doing so would require infinite energy. As an object moves faster and faster, its relativistic mass effectively increases, meaning it requires more and more energy to continue accelerating. Approaching the speed of light becomes exponentially harder. To reach even a significant fraction of light speed, such as 10% of the speed of light, we would need unimaginable amounts of energy. Let's imagine a relatively small interstellar spacecraft with a mass of about 1,000 tons. To accelerate that spacecraft to just 10% of the speed of light would require roughly the same amount of energy that humanity produces globally over many years. And that energy would only accelerate the ship. You would also need the same amount again to slow down when reaching the destination star system. Energy quickly becomes the first major wall blocking interstellar travel. Then there is the problem of propulsion. Chemical rockets, which power most spacecraft today, are extremely inefficient for long-distance space travel. They require massive amounts of fuel relative to the payload they carry. For interstellar journeys, chemical propulsion is essentially useless. More advanced propulsion ideas have been proposed, such as nuclear fusion rockets, antimatter engines, and laser-powered light sails. While these technologies could theoretically reach higher speeds, each comes with massive engineering challenges that may never be solvable. Fusion propulsion requires sustained controlled fusion reactions, something humanity still struggles to achieve even in stationary reactors on Earth. Antimatter propulsion would require storing large quantities of antimatter safely. But antimatter is extraordinarily difficult and expensive to produce. In fact, all antimatter ever created by humanity would barely power a light bulb for a few minutes. Producing enough antimatter to power a starship would require technological capabilities far beyond anything we can currently imagine. Even if we solved propulsion and energy, another terrifying problem appears: interstellar dust. Space between stars is not completely empty. It contains tiny particles of dust and gas. At normal speeds, these particles pose little threat. But at relativistic speeds, even a grain of sand becomes a deadly projectile. A tiny particle striking a spacecraft traveling at a significant fraction of the speed of light would release enormous kinetic energy similar to a powerful explosive. Over a journey lasting decades or centuries, a spacecraft would likely encounter thousands of such particles. Protecting a vessel and its passengers from these impacts becomes an enormous engineering challenge. Then there is the issue of time. Even if we could build a spacecraft capable of traveling at 10% or even 20% of the speed of light, the journey would still take decades. A trip to Proxima Centauri at 20% of light speed would take more than 20 years just to arrive. Including acceleration and deceleration, the total mission could last 40 to 50 years. This raises enormous questions about human survival. Would astronauts spend their entire lives inside a spacecraft? Would we send multiple generations of humans, creating so-called generation ships where children, grandchildren, and great-grandchildren live and die during the journey? Such missions would create complex social, psychological, and biological challenges that we have never experienced before. Isolation, limited resources, and closed ecosystems would push human society to its limits. And even if a crew survived the journey, another problem awaits when they arrive. Radio signals also travel at the speed of light. A message sent from Proxima Centauri would take over for years to reach Earth. Any emergency, malfunction, or unexpected situation would have to be solved completely independently. The crew would effectively be alone in the universe. Some scientists have proposed exotic solutions such as warp drives or wormholes. Warp drives, popularized by science fiction, would theoretically work by bending space-time itself. Instead of moving a spacecraft through space faster than light, the ship would ride inside a bubble where space itself moves. Similarly, wormholes are hypothetical tunnels connecting distant points in space-time. While these ideas appear in real theoretical physics equations, they come with severe problems. Both warp drives and stable wormholes require forms of matter with negative energy density, often referred to as exotic matter. So far, no known physical process can produce or sustain the required quantities of such matter. Even if exotic matter exists, the amount needed to create a usable warp bubble might be comparable to the mass of entire planets or stars. In other words, the technology may be permanently beyond our reach. Another major issue is cosmic radiation. Outside the protective magnetic field of Earth, astronauts are constantly exposed to high-energy radiation from the Sun and distant cosmic sources. On long interstellar journeys lasting decades, this radiation exposure could become deadly. Shielding against radiation adds more mass to the spacecraft, which in turn requires more fuel and energy to accelerate. Every solution creates new problems. Then there is the fundamental question of motivation. Interstellar travel is incredibly expensive and dangerous. Colonizing other star systems would require transporting large populations, ecosystems, equipment, and infrastructure across trillions of kilometers. For comparison, humanity has not even established permanent settlements on Mars, which is relatively close on cosmic scales. If colonizing our nearest planetary neighbor remains enormously challenging, the idea of colonizing planets orbiting other stars becomes almost unimaginable. Some scientists believe robotic exploration might be the only realistic form of interstellar travel. Small robotic probes could potentially be accelerated using powerful lasers to a fraction of light speed. Projects such as Breakthrough Starshot aim to send tiny spacecraft toward nearby stars within a few decades. These probes would weigh only a few grams and could reach speeds around 20% of the speed of light. Even then, the mission would be extremely difficult and would provide only limited data during a brief flyby. Human passengers would remain impossible with this technology. So where does this leave humanity? It may be that the stars will always remain distant lights in the sky, beautiful, mysterious, and forever out of reach. Instead of spreading across the galaxy, our future may be focused closer to home, exploring our own solar system, building habitats around planets and moons, and perhaps creating massive space habitats that orbit the Sun. The universe is unimaginably large, and the laws of physics place strict limits on what is possible. Interstellar travel is not just an engineering challenge. It may be a boundary written into the fabric of reality itself. But history has also shown that humanity repeatedly overcomes what once seemed impossible. New discoveries in physics could change our understanding of the universe in ways we cannot yet imagine. For now, however, the cold truth remains. Between us and the stars lies an ocean of distance, energy, time, and physics that may never be crossed. The dream of traveling to other star systems continues to inspire scientists, engineers, and dreamers alike. But according to the laws of physics, as we understand them today, humanity may never truly become an interstellar species, and the stars may remain forever beyond our reach.